So let's get started here. Now, Aristotle we really don't cover, but I just, it's not one that you really need to know, but just mentioning, because he was up there with Democritus in terms of philosophy, the first real idea of what matter was really about like the four elements: water, fire, wind, and or air, and earth, kind of like the Avatar, element. I'm sure you've seen that show. But that was the first kind of idea of what, was the existence of matter. Not too important. Then Democritus, though, he was important. Democritus you did read about, because he, even though he wasn't a scientist, he was just a philosopher, didn't have, the ability to do experimentation and have actual data, came up with some really great conclusions about, what matter is, just by thinking about it. He took a mortar and pestle, which is, like a grinder, and he sat there and would grind up the, rock into little particles, and that made him start thinking about how, matter could be constructed of these small, tiny particles. We actually got the word atomos from Democritus, which is Greek for indivisible. Greek for indivisible, and that, is the word that the atom came from. So atomos. He also believed through his, philosophy and thinking that atoms are solid, homogeneous, indestructible, indivisible, come in different sizes and shapes. Okay, they can combine, but doesn't actually change the atoms themselves when they combine with other atoms. Didn't really use the word compound yet, but kind of had those ideas. Couldn't really prove it though, so that was kind of an issue. Then we have Dalton, and Dalton is one that they like to ask on the SOL. Dalton, he had his 4-point atomic theory, and he also thought it was tiny spheres. He called it the billiard ball model, like solid sphere, okay, with perfect elasticity and indestructible, indivisible. Once again, kind of same lines as Democritus. But looking at his 4 points here, the first one, all matter is composed of small, indestructible particles called atoms. Well, we can actually break the atom apart now, so they're not indestructible anymore. So that part is technically wrong now. The idea that matter is not created or destroyed, that's just altered, that one still holds true. All atoms of a given element are identical. Well, that one's not true anymore. We do know those, you're going to learn about them again today, but those things called isotopes and ions, where they have different numbers of neutrons or different numbers of electrons, but they're still, atoms of the same element. So not all atoms of the same element are completely identical. So that one's not really true. Atoms of different elements have different properties. That still holds true. We know that. We'll get more into their properties and why they have certain properties based off of their group and so forth. Chemical reaction, atoms separated, combined, rearranged, but they maintain that conservation of mass. It's not created or destroyed, it just gets altered. And later on, he found that, he was playing around with the numbers and figured out the whole number ratio idea of how atoms can combine. And he called that the law of multiple proportions. So an example of that law of multiple proportions here, we have carbon monoxide, which is CO, carbon dioxide, which is CO2. Okay? Now, basically just saying within the two different compounds here, CO has 1 carbon and 1 oxygen, CO2 has 1 carbon to 2 oxygen, so the ratio would be 1 to 2 here for carbon monoxide to carbon dioxide. And you can do a lot with this math. It's more like an AP level kind of thing, and figure out, you can figure out unknowns using the math if you have a machine that will break it up into its elements, and based off of those amounts you can figure out their chemical formulas and so forth. Some of his drawings, not really applicable today, but back then, this is kind of interesting. We still use these circle representations for atoms. We combine them to make compounds, as you can see on the next page. This was his, like an actual historical document. I know you see these like in history a lot, we have to analyze. But as you see on some of these, he actually tried to like put them together like compounds. Which is kind of cool back in that day with not a whole lot of technology to experiment with. These were really great ideas of the time. But it was an evolving process. It wasn't just like instantaneous that we came up with the current quantum mechanical model we have today. So the process continues to evolve because of J.J. Thompson. You guys read about him. He's the cathode ray guy. So what do you really need to know about Thompson? You need to attach cathode ray guy. He did the cathode ray tube experiment, and he discovered the electron. Those are the main important things about Thompson that you need to know. He did the cathode ray experiment, and we're going to show you quickly what actually he did. But he discovered the negatively charged particle that we now call the electron. He didn't call it an electron. He called it a corpuscle or something. But we call it the electron today, the negatively charged particle. And let's show his cathode ray. So he had a cathode ray tube set up like so. The negative side and the positive side of the tube, and he had a wire connected so that he could run electrical current through it. All right, so he's sending his current through, passing the electrical current through. Appears to move from the negative end to the positive end. And if you know anything about electrical energy, it's really a stream of electrons anyway, so that makes sense that they're going to be attracted towards the positive end. Okay? However, he added an electric field to it, where he put these plates surrounding the tube. He put a positive plate up here, and he put the negative plate down here. Okay? And as he sent the current through, basically it started to veer off towards the positive plate, as you see it sloping up towards the positive plate here. So basically from that experiment he could conclude that the particles from the electrical current had negative charges because they were attracting to those positive charges. As the positive and negatives, opposites do what? They attract. Good. Like the north and south ends of magnets, those are opposites, they attract. What if we put two positives together? What should they do? They would repel. Okay? Likes repel. Like charges are going to repel, like negative, negative, or positive, positive. And the ones that are opposite will attract. Okay? So that was important. The way that's actually what he demonstrated. His model is called the Plum Pudding model. You do need to know that too, right? Plum Pudding by his name. Now, we never use this, well, I don't know. Has anybody in here ever eaten plum pudding before? Ever heard of it? Apparently, back in Thompson's day, it was probably one of the best desserts you could possibly have. Plum pudding, basically, you know, we had the idea of the pink stuff up here was the pudding, and the little yellow ones up here, these guys, those would have been the little fruit or the plums that were in the pudding. So I like to think of it more as like an M&M blizzard, the ice cream with the M&Ms in it, you know. That's how I like to think about it, but they actually call it the plum pudding model. The pink stuff is all positive, like the whole pudding part is all positive, and then the little plums that were in between, those would be considered the negative charges, evenly distributed throughout the entire pudding. Except if you want to, you know, modernize it a little bit, the ice cream, you put M&Ms in the ice cream, the M&Ms could be like the plums, the ice cream is like the pudding part, and you have kind of the same concept here where it's evenly distributed throughout, you know, no centrally, you know, charged part. Okay? A bunch of positive stuff with electrons that are able to move around in it. So that was his idea. Plum pudding model. Now Rutherford. Hopefully you found Rutherford on your periodic table, Rutherfordium, because he's named, you know, an element's named after him. He came up, his claim to fame is the gold foil experiment. So if you want to write that down, he's important because he did the gold foil experiment. Gold foil experiment, he gave us two conclusions, which I'll go over in just a minute. But Rutherford, gold foil experiment, let me show you what he did, and then we'll go over his two conclusions that you need to know. He oversaw Geiger and Marsden carrying out his famous experiment. They fired helium nuclei, which are alpha particles. Helium nuclei are just 2 protons and 2 neutrons, so these guys have positive charges, and they're going to, you know, be sent through the atoms here, and we're going to see what happens. Although most of the positive charged particles, these alpha particles, went through the very thin gold foil, about 1 in 10,000 actually hit and deflected. So let's talk about what that means. So here he has his lead block. The lead block's going to shoot it out of here. Here's your thin amount of gold foil. It's a very thin layer, and it has this screen around it so that it would, you know, measure the deflections or measure the beam of the alpha particles. So this is what he expected. They were all just going to go straight through, because if it's the plum pudding model, it's evenly distributed, nothing's going to bounce off, it should be all fine. Okay? This is what he got. So you still have a good majority going through, like there's still a thick amount going through, but you see some deflections in different directions. Okay? Now let's think about why some of them might deflect. This is how he explained it, that most of the atoms are empty space, but there must be this dense positive region. The dense positive region in the middle. He didn't call it a nucleus, that gets, you know, the names later, but 2 things he decided. Atom is mostly empty space, but it has a small positive center. Okay? That positive center, we now call this part the nucleus today. Gives us our nuclear model. Okay? And let me show you why in just a second. As those particles were going through the gold foil, most of the empty space ones just went straight through. But occasionally, a positive alpha particle would run into a what? It would run into a positively center and deflect. Because positives and positives, like we just said, repel each other. So it would deflect and move off. And that's where we came up with, or he came up with, the nuclear model. Okay? That the electrons were in this outer space area, not taking up really any volume or space. But we had this densely, positively charged center, and that's where those alpha particles would bounce off. Like so. As you see, if we were sending them through the atom here, most of them would go, some of them would hit like a direct hit, like this guy hits a direct hit and totally bounces back. This one kind of hits, but it bounces and deflects to the, you know, downward. This one kind of gets veered off, okay? So some of them would directly hit, go back the other direction. Some would partially hit and deflect off in either up, down, or around, okay? But that was the nature of the gold foil experiment, okay? So like we said, he used uranium. Since the mass is evenly distributed in the gold atoms, the alpha particles should go straight through. That was his original hypothesis. Proven wrong, though, because the gold foil, you know, those atoms actually had some centers where they deflected. So he came up with the planetary model, or he's given credit for a planetary model. The idea where there's like the sun in the middle and then all the other ones are around, those being the electrons. The electrons would circle around this positively charged nucleus. That's the idea of the planetary model. Okay? Now, once again, you know, what were his 2 conclusions? The atom was mostly empty space, and it had a positively charged center. Very important. Those are the 2 things you need to know about the gold foil experiment. That was Rutherford's, and came up with this nuclear planetary model with the nucleus center. Now for Milliken. Milliken, he gave us the charge and mass of the electron. That was his claim to fame. He did this oil drop experiment, which is pretty complicated and has a lot of physics in it. And you can see the apparatus right here. very complicated, but through a lot of the calculations and applying magnetic fields and so forth, you're welcome to click on the PowerPoint and watch his simulation video, but it's pretty complicated. But basically gave us the mass and charge of the electron, which is kind of important to know. It's very, very small. It's negligible. Okay, so it barely has any mass at all that we say it's basically zero. Okay. As you can see here, 9.1 times 10 to the minus 28 grams. That's a really tiny number. Very tiny number. That's the mass of an electron. And his charge analysis, when he eventually got through it, basically was a full -1 charge. So keep that in mind. Mass and charge of the electron, that's what Milliken did for us. Very tiny number. You don't need to really know the exact mass of the electron, you just need to know that it's basically zero. Okay, so now our modern view, we're going to get into the quantum mechanical model with the electrons in Unit 3. However, basically there's this nucleus in the center that has positively charged particles, as well as the neutrons. The neutrons are neutral. The electron cloud is this region, and because the electrons basically have no mass, we consider it almost like empty space that the electrons go around. So that's pretty much what we're going to be talking about now. We're focusing more on the nucleus, though, for this unit, and the protons and the neutrons.